I've mentioned earlier that it's extremely common for the AP exam to include an FRQ that covers differential equations. And in the analytic introduction to differential equations, we did one from, I think it was 2013, that requires separation of variables. That was actually on the AB exam. This one might be on both, I'm not sure. But this is using a slope field. This was the 2015 number 4 FRQ. And you'll notice that just like the example we did in the last video, this differential equation is non-separable. There's an x term and there's a y term, and they're separated by a minus. I'm not able to write this as a product of two functions, one of x and one of y. So I'm kind of forced to do this analytically. So they ask us to sketch a slope field using just the 6 points provided. So what we'll do is evaluate the slope at 0, 2. So dy dx at 0, 2 is equal to 2 times 0 minus 2. And dy dx evaluated at the next point over, which is 1, 2, that's going to be 2 times 1 minus 2, or 2 minus 2, which is 0. So we'll have a slope at this point, let's zoom in on this, a slope at this point of -2. And as I mentioned before, accuracy isn't super important, but we definitely want to be shooting for this point down here, because that would be where we would go if we were to travel by a slope of -2. So I'm going to kind of use that as my guide and just draw that much. Now I'm going to get rid of that circle because it's not really part of the slope field, but it was just something that I was aiming for. And then our slope of 0 is going to be at this point right here. That one we really want to make sure is completely horizontal. We don't want any doubt in anyone's head that that might be sloping upwards or downwards. Okay, and we'll just kind of do the same thing for each one of these points. When we look at 0, 1, that's going to give us a slope of -1. So that actually is going to aim for this exact same point from 0, 1 and from 0, 2, where both of those slopes aim towards 1, 0. 1, 1 will give us 2 minus 1 for a slope. That's going to be a slope of 1. So at this point, we're aiming towards the origin. They don't put points on the x-axis for whatever reason, so we don't have to worry about them. At 0, -1, we have 0 minus -1, so that's going to be 0 plus 1, or 1, so that's going to be this point right here. Notice that this line is also, this slope is also aiming for the point 1, 0, so it looks like every single point on the y-axis is going to aim towards this point. That's not necessarily important, but kind of interesting. And then at 1, -1, we're going to get 2 times 1 minus -1. That's going to give us 3. That's going to be a fairly steep graph, the steepest one we have on this itty-bitty rectangle of grid. So make sure it's positive, make sure it's definitely steeper than the 1 over here. And that's really all they're looking for, I think, when they ask to graph a slope field. Okay, you might want to put m equals -2 here and m equals 0 here, m equals -1, m equals +1, etc. I don't think that's required. I think that kind of clutters up your graph, but if you want to, you can. Now, part B asks us to find d squared y dx squared with respect to x or in terms of x and y. So how does that work? Well, that's the second derivative. So let's start by writing down the first derivative. That's dy dx equals 2x minus y. Now we know from past experience that d squared y dx squared is the same thing as taking the derivative with respect to x of dy dx. That's what the second derivative is, right? You take the derivative of the first derivative. So we take the derivative of y with respect to x, and then we take the derivative of that with respect to x. So we're going to take the derivative with respect to x of 2x minus y. And that's fairly straightforward because it's just two terms. 2x differentiates to 2 with respect to x. And then minus, well, the derivative of y, this is 1y raised to the first power. Power rule tells us we're just going to change that to a 1, but then don't forget the chain rule. We're going to multiply that by dy dx. All right, so that is the second derivative. 2 minus the first derivative is the second derivative, but it asks us to have our answer in terms of x and y. So we don't want to leave dy dx in our answer. We're going to say that this is equal to 2 minus dy dx, which is 2x minus y. And that's fine. We could leave it like that, but it's probably better to go ahead and distribute the negative. 2 minus 2x minus negative, or plus, y. That is dy dx in terms of x and y. It asks us to determine the concavity of all solution curves for the given differential equation in quadrant 2, and give a reason. Quadrant 2, we know that quadrant 2 means that x is negative and y is positive. That's true of every single point in quadrant 2. Notice that we have a positive value minus 2x. Well, if x is negative, then subtracting 2x is going to be subtracting a negative value. There's a double negative. It's going to be adding something as well. And then plus y. Well, if y is positive, then we're adding here as well. So each of these three terms will be positive. So we know that because x is less than 0, negative 2x is greater than 0. So we know that 2, which is greater than 0, plus negative 2x, which is greater than 0, plus y, which is also greater than 0, is three positive values. So that when we add them up, we get something that's greater than 0. The concavity, therefore, the concavity is upward for all solution curves in quadrant 2. All right. So that's going to be useful for part B, or part C, I would imagine. Let y equal f of x be the particular solution to the differential equation. Notice that this is, again, a non-separable differential equation right here. So we cannot find this equation for the particular solution. We're not expected to. But based on what we already know, we should be able to figure out whether f has a relative minimum, maximum, or neither at x equals 2. First thing we would want to do is consider what is f prime of 2. Well, f prime of 2 is dy dx evaluated when x equals 2 and y equals 3. Why 3? Because it tells us that that is the point in question. So we can evaluate this and get that 2 times 2 minus 3, that's 4 minus 1, minus 3 rather, which is 1. So that means that the slope at the point 2 comma 3 is 1. So we can actually stop there and say, wait a second, this is a differential equation. This is a differentiable function. We know it is because the derivative exists. And the slope at this particular point is 1. So we don't have a max or a min, because if we have a differentiable equation, then a max or a min must have a derivative of 0. So we would say, because 1 does not equal 0, f of 2 equals 3 is neither a maximum or a minimum of y equals f of x. Okay? It would have been a little bit more interesting if, when we had found dy dx, we got a value of 0. And then we would actually get to use the fact that this is a concave upward graph. If we have a concave upward graph and a derivative of 0, a slope of 0, then that would be a minimum. But since we're not at this point, we're at a point where the slope equals positive 1 instead, then we're actually not looking at a max or a min. We're just looking at some point on the curve. There's actually a fourth part to this FRQ, which says find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay, so this is a different particular solution, not the one talked about in part C that says y equals f of x, because this, well, maybe it is the same one, but this one is just some curve. This one in particular is a curve that is a line. Okay, so we recognize this to be a linear function. So given that, we know that dy dx has to equal a constant. Specifically, dy dx has to equal the slope m of the line that is the solution. Okay, so we furthermore know that that would imply that if we took the second derivative, we're going to get 0, right? A line has concavity of 0. It doesn't concave up or downwards. It's always pointing in the same direction. But you might recall that we know what the second derivative is. The second derivative is 2 minus 2x plus y. So 0 is equal to 2 minus 2x plus y. So this equation right here is a linear equation. It is the solution that that satisfies the differential equation. So we can just solve for y, because that's what it says right here, y equals mx plus b. So we'll subtract the 2 to the other side, we'll add the 2x to the other side, and we'll get 2x minus 2 is equal to y. Therefore, it looks like m has to equal 2, and b must equal negative 2. There are some other ways we could do this, but that to me seems like a pretty efficient way of doing that problem. And that was all the parts of the FRQ, but I decided to add a new one because I just couldn't resist. Not part of the original FRQ, but let's look at a new solution, y equals g of x, and that goes through the point -1, -2. So let's take a look at this. This is the same question as part C. Does this point have a local maximum, minimum, or neither? And we can answer that the same way, right? We know that g prime of -2 is equal to dy dx evaluated at this point, at the point -1, -2. And that is, if we were to I don't have the differential equation on the screen at the moment, but 2x minus y. dy dx equals 2x minus y. So if we look at 2x minus y, we'll get -2 minus -2, which is 0. Aha! So we don't know what exactly is going on here until we consider that second derivative. So we're going to evaluate the second derivative, also at -2, -1, -2. Our second derivative is 2 minus 2x plus y. And when we evaluate that, we get 2 plus 2 minus 2, which is 2. And that's a concave up graph. Okay? So if we have a slope that's equal to 0 and a concave up graph, then by the second derivative test says g of -1 is a relative minimum of y equals g of x. And we can prove that. Well, we did prove that analytically with all of this work over here. We can convince ourselves of that with a little picture, a concave up graph, where the slope is equal to 0. That is going to be a relative minimum.